So now we want to look at geometric sequences, and let's follow the same path we did for arithmetic sequences. Okay, so the dog's very excited about it. We want to look at y equals 3 times 2 to the x. And let's convert to function notation. So f of x equals 3 times 2 to the x. And basically, by converting to function notation, I'm guaranteeing that the shape will be a function. And we happen to know that exponential curves look like that. And even though they get very steep up toward infinity, if I pass a vertical line through this curve at any point, I'm only going to intersect one time. And that means I'm dealing with a function. So let's fill in values. Let's look at f of minus 1. Well, that's 3 times 2 to the negative 1, but that just means put 2 in the denominator, so 3 halves. And if I were to plot that, I'm going to, on the y-axis, I'm going to use intervals of 2. So it'll be 2, 4, 6, 8, 10. And on the x-axis, I'm going to use 1, 2, 3, 4, 5. So 3 halves. If this is 2, then 3 halves would fall right about there for negative 1. Now the f of 0 is 3 times 2 to the 0. 2 to the 0 is 1, so that just equals 3, 2, 3. The f of 1, 3 times 2 to the first power. Well, that's just 2 times 3, which is 6. So 2, 4, 6. The f of 2 is 3 times 2 squared, which is just 4 times 3, which is 12. 2, 4, 6, 8, 10, 12. And I think I'm out of values on the graph. Let's just see. 3 times 2 cubed. So 2 cubed is 8 times 3 is 24, and that's off my graph. So if I were to graph this as a function, it would look like that. And that's exactly what we expect from a function or from an exponential graph. But we don't want to graph this as a function. We want to look at just the output values. And looking at just the output values, remember, well, that didn't help. This is 12 as an output. The output for this next point down is 6, and then 3, and then 3 halves. So if I were to put these into a sequence, I would have the first would be 3 halves, the second would be 3, the third is 6, the fourth is 12, the fifth is 24, and if I kept adding function values, it would go on and on. Well, let's look. How do these differ? Remember when we were learning about exponential models, we looked at tables where the input values incremented forward by +1, +1, +1, but the output values incremented forward by multiples. So what would it take to multiply? What would I have to multiply 3 halves by to get 3? Well, I would multiply it by 2. The 2's would cancel and be left with a 3. Let's see if it carries all the way through. Times 2 equals 6, times 2 equals 12, times 2 equals 24, on and on and on. So, just like with an arithmetic sequence, we have a name for this that's different than the name when we're dealing with an exponential equation. Remember, this is the exponential base when we're dealing with an exponential, but when we're dealing with a geometric, we call it the common, just like before, ratio. So it's a common ratio. Each of these values are still called terms, and they have the same label. The first term is the a sub 1, the a sub 2, the a sub 3, the a sub 4, the a sub 5, and on and on and on. And just as we did with arithmetic sequences, we have a formula that can be used to find the nth term, whichever term we want to find in the sequence if it goes on and on and on. whichever term we want. And the formula is a sub n equals a sub 1, the first value, times r, the common ratio, I should say that, letter r, raised to the n minus 1 power. Let's do an example. So we want to determine whether the sequence is arithmetic or geometric. So 81, 77, 73, 69, and 65, on and on and on. Is this geometric, arithmetic, or neither? Remember, it has to either have the plus 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 pattern, in which case it's arithmetic, or the times 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 pattern, in which case it's geometric. If it's neither of those, then it's neither of those. So let's see what we have. So 81, if I want to move from 81 to 77, let's try by addition first. So 81 to 77 would be 4. So I'm subtracting 4. If I subtract 4 from 77, I get 73. This is looking very arithmetic. From 73 to 69 is subtract 4, and again subtract 4. So I know that this is an arithmetic sequence. And I can identify the next couple terms. 65 take away 4 would be 61. Take away 4 would be 57. And then I could just go on and on from there. Let's look at another example. This is 3, 6, 12, 24, and 48. Again, we recognize this. 3, 6, 12, 24, it just has an extra term in it. We know that the geometric series for this is times 2 times, we know that the ratio or difference, the common separation, would be times 2 times 2 times 2. So in this case, we're looking at times 2 all the way across. So this is a geometric sequence. And if we needed to find additional terms, 48 times 2 is 80, 96. I'm not going to do that one. On and on and on. I'm not going to go past that. I guess 180 and 12 should be 192. I'm thinking that's true. Okay, that one, now I'm definitely not going past that. Okay, let's use this sequence just as we did before and determine a formula and see how closely it matches the original formula I used to create that sequence. So if I'm given these numbers, this set of numbers, I want to use the formula a sub n equals a sub 1 times r to the n minus 1. So in this case, that would be a sub n, or the nth term, would be the first term, which, let's use this version, 3/2, times the common ratio, 2 raised to the n minus 1. So just like before, let's do a little arithmetic or a little algebra. That's 3/2 times, and I'm going to use parentheses now, this would be 2 to the n times 2 to the minus 1. Remember our exponent rules. When you add or subtract exponents, or when you add exponents, you're actually multiplying the same base to the two different exponents. And then 2 to the minus 1 is really 3/2 times 2 to the n over 2. And if I multiply all of that out, I get a formula, 3/4 times 2 to the nth power. So it's not exactly the same thing. I got the same base or common ratio. That part's the same, but the 3/4 is different. This one is 3 and this is 3/4. But remember, this is a case where when we're dealing with sequences, we're not allowed to choose values that are integer value, that are not integers greater than 0. So n has to always be an integer greater than 0. So let's look at what happens when I plug in. I can't plug in -1 and I can't plug in 0. The first integer I can plug into my new formula is a +1. Let's see what I get out of that. So let's plug in, let's say a sub n equals 3/4 times 2 to the first power. But that's just 3 times 2 over 4, which is 2's will cancel, which is 3 halves. So the first term, plugging in 1, gave me the first term that's back here. I didn't get a point up here somewhere that could be a coordinate. I had to use 1 to get me back here to that first term. So the formula turns out to be a little bit different when I get there. Let's do another one, a sub, and so we can call this a sub 1. A sub 2 is 3/4 times 2 squared, but that's just 4, which cancels with the 4 and equals 3. So the second integer gives me the second term in my sequence. A sub 3, just because we're having such a good time, is 3/4 times 2 cubed. Well, that's just 3 times 8 over 4. 4's cancel, leaving a 2. So that equals 6. Indeed, I got 6. So the third integer is going to give me the third output value. And then one last step in the example is we're asked in this formula, right? We're asked from this to find the a sub 10. Wow, Stanley's really into sequences, isn't he? So a sub 10 is 3/4 times 2 to the 10th. Okay, 2 to the 10th. I'm actually not going to spend any time on this, having you watch me work with a calculator or kind of fumble my way through this. I'm going to tell you what it is. But 2 to the 10th times 3 divided by 4 equals 1,536. So I can find the 10th term. If I want the 11th term, that's a sub 11 would be 3/4 times 2 to the 11th, and so on.